Hello everyone, in this video we're going to talk about power series. So a power series is going to be a series of the form sum from n equals 0 or n equals 1 to infinity of an, where an is the sequence, times x to the n, where x is it can be any number and is power to the n. And so this is going to be like a polynomial arrangement where we have a sum of the form a0 plus a1x plus a2x squared plus, and we're going to get to the number x to the n, and we're going to continue adding numbers. Now, for each number that we substitute x, we might be able to get a series of constants that will give me a series that might be convergent or divergent. And so, for example, if we're given an to be 1, if we just fix an to be 1, and we replace x equals 2, then we're going to have this series here, which is a geometric series and is divergent. Or if we do like x equals 1/2, then we're going to have the series from 1/2 power to the n, and that series is actually convergent. So notice that a power series is very dependent on the values of x. If you give certain x, it could be convergent. If you give certain x, it could be divergent. Now, we need to check for what values of x we're actually going to have a convergency. And so in a more general sense, I can consider a power series around a given point A. Before, when we just had x to the n, we were considering that we have a power series centered around 0. But you can center the power series around any number that you want. So I can have a general power series from the form sum of n equals 0 to infinity of an x minus a power to the n. Now, if we assume that x equals a by chance, notice that this is going to become 0. And so that's going to be just a series of 0, and it's going to be convergent, of course. But if x is different from a, then it becomes more interesting, and there's going to be a number r bigger than 0, so that the series is going to be convergent in an interval of close to a. So an interval a minus r, a plus r. That interval is called the convergence interval of the series. And r is going to be called the convergency radius of the series. Now, this is a theorem in general, and when we have a power series, we only have 3 situations. We can have that the series converges only when x is equals a, because in that case it's just the series of zeros, the sum of zeros, and that's going to be finite sum, so it converges. The series is going to be convergent for all x, so that means that the radius of convergency here is going to be infinite. There's not going to be any restriction at all for x. And the third case, which is the most normal case, and is that there is a positive radius of convergency, so that the series converges if the absolute value of x minus a is less than r. It is going to be divergent for any number that is outside of that range, for absolute value of x minus a bigger than r. When we are trying to find the radius of convergency and the interval of convergency, then we are going to use the ratio test or the root test to find these intervals. If r is equal to 0, we're in the first case, where the series converges, we're only at the point where it's centered. If r is infinity, then it converges for all x. And if we have a normal interval of convergency that is just a finite number, then we're going to have to check what happens with the endpoints. Okay, so we need to find out what happens with a plus r, and we need to see what happens with a minus r. Those points are not guaranteed to be convergent, so we need to check for those. So now let's check some examples of this. Now let's use the root test and the ratio test to find the interval and radius of convergency for the following series. The first one is just simply the series of x to the n. So the way that we're going to go about this is if we're using the ratio test, we're going to go with an plus 1 x to the n plus 1 over an x to the n. So that's how we're using here the ratio test. But what happens here? An is actually just 1. So this is just simply the limit when n goes to infinity of what? Since this is 1, this x to the n cancel with this x to the n plus 1, and it's only left absolute value of x. So this is just going to be absolute value of x. This is going to be my limit. And by the criteria of the ratio test, this converges if the absolute value of x is less than 1. So this limit is less than 1. So this implies that my radius of convergency here is 1. Clearly this is centered around 0. So the interval of convergency is going to be 0 minus 1, 0 plus 1, or simply minus 1 to 1. And that kind of takes care of the initial step when we're trying to find the interval and the radius of convergency. Now we got to verify what happens if we just do the series on the extreme. So if x is equals minus 1, we actually have the series from n equals 0 to infinity of minus 1 to the n. And we really don't know what this is. We really don't know if what this is going to be. So we cannot say that even the partial sum is going to something. So this is divergent. And in the same case, if x is equals 1, then we're going to have n equals 0 to infinity of 1 to the n, which is 1. So this is just infinity. And so it's going to be divergent as well. So we're not going to be able to include the extremes in there. And that's the result. The radius of convergence is 1. The interval of convergence is minus 1 to 1. Now let's move on to the next example. For the next example, we have the series from n equals 1 to infinity of x minus 3 to the n over n. So this is essentially here an is equals 1 to the n. So if I'm doing ratio tests, which is going to be the easiest to do here, I'm going to do an plus 1 x to the n, here's x minus 3 to the n plus 1 over and x minus 3 to the n, absolute value. And now, so I pretty much plug whatever this is, which is 1 over n plus 1. So this is absolute value of 1 over n plus 1, x minus 3 to the n plus 1 over 1 over n, x minus 3 to the n. And then now I simplify. And when I'm simplifying, this is going to be limit when n goes to infinity of n over n plus 1. And this is going to be just simply x minus 3. Since I lose the power to the n. And so this is going to be x minus 3 absolute value times the limit when n goes to infinity of this n over n plus 1. Notice that this is an infinity over infinity limit, but you can kind of factor the n, and you're going to see that this is 1 over 1 plus 1 over n. And so this is just x minus 3 limit n goes to infinity of 1 over 1 plus 1 over n. And this goes to 0 and this goes to 1. So this is just simply x minus 3, an absolute value. Now to be convergent, then we need to have that x minus 3 has to be less than 1 so the series converges. And so that implies that the radius of convergence in this scenario is going to be 1. and the interval of convergency is just going to be 3 minus 1, 3 plus 1, since it's a center around x equals 3. So this gives me the interval 2 to 4. Now, if I'm willing to go and check what's going to happen with x equals 2 and x equals 4, so I can check here. So if x equals 2, then we have the series from n equals 1 to infinity of minus 1 to the n over n. And this is the alternating harmonic series. And so this converges by the alternating series test. If x equals 2, then, if x is equals 4, which is the other n, then I'm going to have that this is n equals 1 to infinity of just 1 over n, which diverges because it's the harmonic series. So this means that the interval of convergency is going to be really 2 close, 4 open. And the radius is just going to be 1. Now let's move on to the next example. Now for the third series, we have the series for n equals 1 to infinity of n factorial times x to the n. So as you can see, the an sequence is the n factorial. So here the ratio test is going to be the limit when n goes to infinity of n plus 1 factorial x to the n plus 1 over n factorial over x to the n. In this scenario, notice that we're getting absolute value of x times the limit when n goes to infinity, and we're going to have the absolute value of n plus 1. Since you can easily cancel out the n factorial, since n plus 1 factorial is just n plus 1 times n factorial. And so you're able to cancel out the n factorial. Now the issue with this is that this is going to give me infinity. Okay, and so you might think that this means that getting infinity here means that this is an infinite radius, but it's actually quite the opposite. When we get infinite in the limit, this means that the radius of convergency is 0. And this means that this is only converges for x equals 0. So be careful when you obtain infinity here, and remember that your radius is actually going to be the opposite, which is not something that we had the case to see before. Now let's go to the next example. Here we're going to have limit when series for n equals 1 to infinity of x to the n over 2n factorial. And so the ratio test here is going to give me limit when n goes to infinity of x to the n plus 1 over 2n plus 2 factorial, since that's what plugging in n plus 1 will do here, and over x to the n over 2n factorial. So now let's simplify this out. This is equals to the limit when n goes to infinity of, again, absolute value of x, but we're going to have now 2n factorial times 2n plus 2 factorial, which we can write as 2n plus 2 times 2n plus 1 times 2n factorial. We can cancel out the terms in here, and this is going to give me a limit when n goes to infinity of absolute value of x, or actually let me put this absolute value outside since it doesn't depend in n. So this is absolute value of x limit when n goes to infinity of 1 over 2n plus 1, 2n plus 2. Notice that that's going to give me a 0, since this is 1 over something that goes to infinity. So this is going to give me 0. Now, this again doesn't mean that the radius of convergency is going to be 0. Actually, when your limit is 0, your radius of convergency is going to be infinite. So now the radius of convergency being infinite implies that your interval of convergency is the minus infinity to infinity. So this is convergent for all values of x. So we are in the second scenario that we were discussing before. Last but not least, we have this example here. A series for an n equals 0 to infinity of x plus 7 to the n over 2 to the n. And one of the difference here is that I mentioned that we can use root tests, and we can also use ratio tests to find out what the interval of convergency and the radius of convergency is, but we haven't really used root tests so far. And one of the reasons why we haven't is because we didn't really have a power that we could use where it would be easier to use the root test. This is one of the scenarios where we can actually use the root test, and we can say, well, limit when n goes to infinity of n root of absolute value of a n x to the n is going to be usable. And we have limit when n goes to infinity of, notice that if we have the absolute value here and we take the n root, then we're going to get absolute value of x here. And then now we're going to have n root of, sorry, this is not x but x plus 7. So this is x plus 7 to the n. So now this is x plus 7 absolute value. Limit when n goes to infinity of square root, or sorry, n root of 1 over 2 to the n. And so as is to be expected, the n root is going to cancel out this power n here, and we're just going to get x plus 7 over 2. Since this will be limit when n goes to infinity of 1, which is 1. So x plus 7 divided by 2. Now, this is one of the common situations that you will face when you're finding intervals of convergency. And so notice that in this scenario, we're back to what are the conditions for convergency. So in order to have convergency, we need that this limit x plus absolute value of x plus 7 over 2 is less than 1, because the ratio test is also only going to be convergent when this is less than 1. If it's bigger than 1, then it's divergent. So now we have convergency here when the absolute value of x plus 7 over 2 is less than 1, but that implies that the absolute value of x plus 7 gotta be less than 2, because we move this 2 to multiply to the other side. And so if we solve this inequality, we can also say, well, first and then before solving the inequality, this is giving me the radius of convergency. So this number here is the radius of convergency, and so the radius of convergency will be 2. Now, to find the intervals of convergency, I break apart the inequality. This is x plus 7 is between minus 2 and 2. Well, between minus 2 and 2. I don't really know yet what happens with the endpoints. But this is equivalent to adding 7 everywhere. And so this is going to be minus 7. X is between minus 5 and 9. And so this is my tentative interval of convergency. But I got to go and see what happens now with the edges. So if I plug, let's remember that this is x plus 7 to the n. So if x is equals minus 5, then I'm going to have the series from n equals 0 to infinity of 1, right? Because this is minus 5 plus 7 is 2 to the n over 2 to the n is just 1. And so this is infinite, and this diverges. And if x is equals 9, then I'm going to have now the series from n equals 0 to infinity of 16 to the n over 2 to the n. So this is clearly a ratio. I can see this as really 16 over 2 to the n, or even a to the n. Since this ratio here is bigger than 1, then this is a divergent series as well. This is a divergent geometric series. So none of the extremes is going to work out, and the interval of convergency is just going to be minus 5 open up to 9 open, and with a radius of convergency of 2. And so this concludes the examples for this section, but you have a ton of other situations that can occur when you're doing this, so there's a lot of practice that is needed for this topic.